Hey guys, welcome back to another lecture video for Chem 115. In this lecture video, you'll be introduced to the concept of chemical equilibrium. So let's go ahead and get started. Now, when you guys were studying chemical reactions in the first semester of general chemistry, you may have developed an idea that all chemical reactions will move in the forward direction, such that all of the reactants present in the reaction vessel, for example, a beaker or an Erlenmeyer flask, will be completely consumed during the course of that chemical reaction. And at the very end of the reaction, only products will remain inside that reaction vessel. And so an example of this is a combustion reaction, where our source of our hydrocarbon is going to be CH4, which is commonly known as methane. And so when methane reacts with molecular oxygen, which is present in our atmosphere, in the presence of some type of catalyst, such as a spark, these two reactants will be completely consumed, producing these two products. And so one can say that this type of reaction has undergone completion. In other words, all of the reactants gets converted into products. And so one way for students to demonstrate that a reaction has undergone completion is through the use of this single-headed arrow, typically pointing in the direction of the production of products. Unfortunately, there are many chemical reactions that do not undergo completion. In other words, at the quote-unquote end of that chemical reaction, there is a mixture in the reaction vessel where some amounts will be reactants and some amount will be product. And so for these types of incomplete reactions, if you will, most of them are going to be reversible. And one way that you guys can demonstrate to a reader or an audience that a reversible reaction is taking place is through the use of two single-headed arrows that's typically pointing in opposite direction. Another way for you guys to represent a reaction that's reversible is through the use of a double-headed arrow, such as this. So looking at this example of a reversible reaction, here we can see that reactant A is going to decompose to produce product B and product C. And so one can imagine that as the amount or the concentration of the products increases as the reaction progresses, there is going to be an increased likelihood that the product particles, B and C, will collide. And if they have the correct molecular orientation, and if they have enough kinetic energy to overcome the activation barrier, then the reverse reaction can occur, which allows the reactant to be reformed. And so an example of a reversible reaction that hopefully you guys were able to study in the first semester of general chemistry is the conversion of hydrates to their anhydrous substances. And so the really cool thing about hydrates is that they're typically colored, they're chromatic. And so for this specific example, we have copper 2 sulfate pentahydrate. And so due to the geometry of the crystal and the orientation of these water molecules that surrounds the copper 2 sulfate, the color of this substance, of this hydrated substance, is going to be blue. And so it turns out that when you heat this sample, and so basically heat is being absorbed by the system, this is the reason why it's endothermic, these water molecules that are adhered onto the ionic compound will have the opportunity to evaporate. And so the separation of those water molecules that is adhered to this copper 2 sulfate produces the anhydrous compound, which is just regular copper 2 sulfate, and water vapor. And so heating this sample will turn the color of these crystals from blue to white. And so we can see the forward reaction taking place just by using our eyes, nothing special. And so the reverse reaction can also occur if these water molecules that's present in our atmosphere adhere onto the anhydrous compound of copper 2 sulfate. And so when these water molecules adhere to this white substance, a blue color will reform, informing us that copper 2 sulfate is now hydrated with water molecules. Water molecules are adhered back onto the crystal. And so if you guys are not familiar with this experiment, feel free to check out this YouTube link. Go ahead and start it about a minute and a half. You guys are just watching the last half of that video, just so that you guys can see the conversion of this hydrate from blue to white and white to blue. And so what is this reversible reaction that we've kind of been discussing have anything to do with the main topic of this chapter, which is chemical equilibrium? Well, it turns out that chemical equilibrium is one can say it's a state where for a chemical reaction to achieve equilibrium or to achieve that state, the rate of the forward reaction must be equal to the rate of the reverse reaction. And so when the rate of the forward reaction is equal to the rate of the reverse reaction, overall, the system has reached a state of equilibrium. And so for the remainder of this lecture video, I want to go ahead and further discuss the details of this idea of an equilibrium. But first, we need to understand we need to understand the overall concept of equilibrium before we get into the details. And so to do that, I'm going to go ahead and use this image. And I am going to be representing these piles of rocks as reactants A and B. And I'm going to be representing these piles of rocks, or this area where the piles of rocks are located, as products C and D. Okay. And so here I'm using this very generic chemical equation to describe the reversible reaction between reactants and products. And so now that we understand what these rocks represent, let's go ahead and understand what these ants represent. So notice that these ants are transporting these rocks from the reactant side to the product side. And this other ant is transporting these rocks from the product side to the reactant side. And so we can go ahead and associate the rate of movement of these ants to the rate of the forward reaction and the rate of the reverse reaction. Okay. Now, when we were studying kinetics, hopefully you guys recall that we can substitute or use the rate constant to describe the rate of the chemical reaction going the forward and reverse direction. And so I'm going to go ahead and use K1 to describe the rate of the forward reaction, and K negative 1 to describe the rate of the reverse reaction. And so in our diagram, the piles of stones are going to represent reactants and products, and this ant that's going in the forward direction is going to represent the rate constant K1. And this ant that's going in the reverse direction is going to represent the rate constant K negative 1. It's just the rate constant that's going in the reverse. All right, and so what we're going to do is we're going to create a scenario, and we're going to imagine these ants moving from reactants to products and products to reactants. And what we're going to do is we're going to kind of tabulate their rate of movement in this table that I've kind of written out ahead of time. And so looking at the top row of this table, notice we have time 1, 2, 3, 4, and time 5. And so you guys can imagine these times as snapshots of their instantaneous rates. Okay, so let me go ahead and write that down. So we can go ahead and think about these different times as instantaneous rates. And so they're measurements of how fast these ants are moving at specific time periods. And so it's arbitrary at this point, time 1, time 2, time 3, time 4, and time 5. Where the first row, if you will, is going to represent the rate of the forward direction. In other words, it's the ant that's moving in the forward direction. And then the last row is going to represent the ant that's moving in the reverse direction. All right, so imagine that we are at time 1 or initial time. You can call it time 0 if you want. And so if we're at the initial time, we're going to assume that all of the piles of rocks will be on the reactant side. In other words, we have 100% reactants and 0% products at time 1. And so it doesn't make sense for our ant that's going in the reverse direction to move if there's no rocks to move. And so at time 1, we're going to say that it is moving at 0 steps per second. It's just staying there. There's no rocks for it to move. And so since there's, a lot of rocks at time 1 for this ant to move, it's going to have, this fast rate, right? So just imagine that you're just about to work out. You have all of this energy. And so let's just say that this ant is going to move at a rate of 10 steps per second. And so at another time period, and we're going to call this time 2, this ant is getting a little tired, so it's going to slow down. So it's going to take 8 steps per second. And then time 3, maybe it's going to slow down even more to 6 steps per second. And then finally, it gets tired of running and it's just going at a leisurely pace. And so for time 4 and time 5, it's going at 4 steps per second. So all of this is describing the rate of movement of this ant going the forward direction. And so looking at the ant that's going the reverse direction, once some reactant particles gets converted to product, then some product can finally be loaded onto this ant, if you will, and moved back to the pile of reactants. And so after some period of time in which the amount of products accumulate, maybe the ant that's going the reverse direction is starting slow, right? So maybe 1 step per second. Then, it kind of gets into the mood of things, if you will. And so maybe it starts going in 2 steps per second at time 3. And then it's going to, try to move faster just because, it still has a lot of rocks to carry back. And so maybe at time 4, it's going to be 4 steps per second. And time 5, it's going to be 4 steps per second. And so according to the definition of equilibrium, if we take this analogy and we think back at a chemical reaction, when the rate of the forward is equal to the rate of the reverse reaction, the chemical system is said to be at equilibrium. And so looking at the numbers that I kind of made up, time 4 and time 5 is really where these the rate of the forward and rate of the reverse is pretty consistent and constant and equal. And so here we have like this convergence of rate between forward and reverse. And so we can go ahead and say with much greater confidence that during this time period, the chemical system is at equilibrium. And so for time 1, time 2, and time 3, this specific section, notice how the rates are not the same. And so during these times, the chemical system is not at equilibrium. Okay. And so if we had, time 6, time 7, time 8, and if the rate of the forward direction and the rate of the reverse direction is still 4 steps per second all the way through, then from here on out, the whole system will be at a state of equilibrium. And so hopefully you guys kind of understand my analogy. If not, and if you guys want another visual, or if you want to check out just a different perspective on how equilibrium can be presented, feel free to check out this YouTube video. I believe it's a 3-minute clip, and it's showing how equilibrium can be reached through a tank of water and some cups. All right, and so the definition of equilibrium just describes that the rate of the forward and the rate of the reverse must be equal. And so this definition of equilibrium doesn't really describe, what's going on before equilibrium has reached or has been reached. And so what we're going to do next is we're going to look at 3 different scenarios in which the instantaneous rates, if you will, before equilibrium has been reached. We're going to look at 3 different scenarios in which there are, different combinations in which the instantaneous rates might look like before equilibrium has been reached. And so that's what we're going to discuss next. All right, so for this example, we're going to take A and B as our reactants, C and D as our products. And so everything in blue is going to be the reactants. Everything in purple is going to be products. And so the first scenario that we're going to look at And hopefully this scenario becomes clearer as we progress through this lecture video. And so in this first scenario, the initial and subsequent instantaneous rates are proportional to each other before equilibrium has been reached. And so the rate is proportional to each other until the rates are the same, meaning the chemical system has achieved equilibrium. And so what does this scenario look like? So if we look at this graph, once again, here in blue is representing the reactants, and here in purple it's representing the products. And so if you guys pay attention to the y-axis, it's the rate of the chemical reaction against time. And so we can go ahead and actually, let me take a step back. So if you guys recall from the kinetics chapter, that reactants will be consumed, and it's typically represented as an exponential decay, where products are going to be produced, and the graph that best represents that will be logarithmic growth. And so I'm just going to put a note here. I'm just going to write down the rate of reactants consumed. And then this is going to represent, this purple line is going to represent the rate of products produced. Okay. And so remember that the definition of equilibrium only describes what the rate of the forward and reverse is when it has achieved equilibrium. It does not describe anything about how or what the rates look like before equilibrium has been achieved. And so what we're going to do is we're going to look at, the three different scenarios in which the rate of the forward and reverse might change just a little bit before equilibrium has been reached. And how will that affect the amount of reactants, and how will that affect the amount of products at equilibrium? And so we're going to take the simple scenario for now, where the rate of consumption is proportional to the rate of production before equilibrium has been achieved. And so we can go ahead and draw lines tangent to the curve, which is going to represent the instantaneous rate. And so if I were to draw a line that's tangent to the curve right about here, and let's go ahead and do one for the products, which is right about here, notice that the slopes are equal in magnitude. Or proportional. Okay. And so that's signifying that the rate of the forward and the rate of the reverse, they're pretty much in a equal set pace, if you will. And so if this ant is moving in a specific amount of steps per second, the ant that's going in reverse will be moving at that same rate. Yet they're not at equilibrium yet, just because this is just initial rate. Okay. And so if we keep drawing lines tangent to the curve, so let's do green. So let's just say I'm going to take a line tangent to this point. Give me a second here. So here you can see that if that one doesn't look too well, but that's okay. So notice how the lines are converging. The instantaneous rates are converging as the rate of the forward slows down and the rate of the reverse starts increasing. And so we can do this infinitely until we get to this brown dot. And so when we get to this brown dot, if we take the slope of both reactants and products, the rate of the reactants being consumed and the rate of the products being produced, these two lines will start converging. And so it is specifically at this point where the system has reached an equilibrium. Okay? And so notice how the rates or slope, well, let's just say instantaneous rates, which is represented by slope. So the instantaneous rates converge. And the slope of this line is equal to 0. Okay? And so here, if you want, you can say that the slope of this line is positive 10. The slope of this line is negative 10. I'm just making up random numbers. The slope of this line is going to be, positive 5. And the slope of this line is going to be negative 5. Once again, I'm making up numbers. And as the reaction progresses, at some point in time, the line tangent to the curve will flatline. It's going to look like this, in which the slope is equal to 0. And so at that point, the rate of the forward is equal to the rate of the reverse. And so how does this type of situation, this type of scenario, affect the amount of reactants and the amount of products? Well, in this specific scenario, since the instantaneous rates are proportional both in the forward and reverse, then the amount of reactants and amount of products will look very similar to that of the rate of reactants being consumed and the rate of products produced. And so here, we're going to, it's going to represent this blue line is going to represent reactants consumed, specifically amount instead of rate. And then this is going to represent the amount of products produced. Okay. And so once again, when the rates converge, the amounts converge, and we're going to get a flat line. And so it is at this point where the amount of reactants and amount of products are at an equilibrium. And this is really where we see a chemical reaction not changing at all. And we'll talk more about that when we talk about dynamic equilibrium. All right. And so let's go ahead and look at another scenario. So remember that at equilibrium, the rate of the chemical reaction are equal to each other, but the definition of equilibrium does not describe what's happening to the rates beforehand. And so another scenario that we can come across is such that the initial and subsequent rates are not proportional between the forward and reverse reaction. And we're going to go ahead and look at the scenario where the rate of the forward is much faster initially than the rate of the reverse. And so what we want to do is you want to look at how the differences in the rate of the forward and the rate of the reverse affect the concentration of reactants and the concentration of products when the system has reached equilibrium. Okay? And so all of this is affected. So the concentration or the amount of reactants and products is affected by this idea of initial rate. It's the rate of the chemical reaction before equilibrium has been achieved. And so once again, we can go ahead and draw lines tangent to the curve to better demonstrate this idea of initial rates that are not equal between forward and reverse. So notice that here, this red line for the reactants, the rate for the reactants being consumed is much steeper. So this is a steeper slope, meaning we have a high initial rate. And so I'm going to represent that as K1. Okay. And so if you take a look at this line tangent to this curve, notice how the initial rate is not so steep. Okay, so not as steep as the forward reaction. Okay. And once again, if you want, you can draw in a second point. I'll just do it from here and here. And so if you want to draw an instantaneous, if you want to draw a line tangent to the curve to represent the instantaneous rate at that specific point, you very well can. Okay. And so once again, you guys can see, no, I don't think I did a good job of that last one. Okay. And so you can go ahead and see that the slope or the steepness of, well, I shouldn't put an arrow there, but you can see that the steepness of this line is much more steep than this line. And in other words, the forward reaction is much greater than the reverse before equilibrium has been reached. And so as time progresses, at some point in time, the slopes will converge, the instantaneous rates will converge, and in this scenario, the point of equilibrium will be in this region. So it's kind of lower down. It's kind of lower than the first, right? Okay. So we can kind of imagine that this is the middle point, just as a point of reference. And we can see that where the rates are converging is much lower than the previous scenario. But it doesn't really matter, because it is at this point where the chemical system has reached a state of equilibrium. Okay. And so let's go ahead and understand how a higher initial rate is going to be, how does a high initial rate affect the concentration of reactants and products when the reverse rate is much slower than the forward reaction. And so I went ahead and already drew it. And so, let me see, I'm going to switch to black. And so here we have reactants being consumed. So I'll just put in reactants. And this is going to be amount of products that's being produced. Okay. So please pay attention to the y-axis. So we're talking about amount of reactants and amount of products. And so it turns out that since we have a higher since we have a much faster initial rate in the forward direction than the reverse, at equilibrium, the amount of products produced will be much greater than the amount of reactants. Okay? And so that makes sense. If the forward reaction is happening much faster, so I'll go back to the ant picture. Okay. So if the forward reaction is happening much faster than the reverse, then this ant is able to convert or transport more reactants into the product pile. And so we should have more products when the system has reached equilibrium compared to reactants. And so if the rate of the forward is greater than the rate of the reverse, then the amount of products, and we can go ahead and draw a horizontal line. So notice that it hits this specific point, which is much higher than this specific point. And this purple line represents products, and this blue line represents reactants. So we have a lower amount of reactants once equilibrium has been reached. And I'll go ahead and kind of mark off with a horizontal line. Maybe I'll just do dotted line. And so this is where the system is at chemical equilibrium. Okay. All right. So let's go ahead and look at the last scenario, last condition, if you will. And it's basically a flipped version of this. And so what would happen if the initial and subsequent rates of the chemical reaction are not proportional once again in the forward and reverse, such that the reverse rate of the reaction is much faster than the forward. And so looking at this rate versus time graph, we can go ahead and observe that the initial rate, so I'm going to draw a line tangent to the curve. Notice how that line is much steeper than this line. Okay. And so in this scenario, the initial rate, because it's being taken, this line that's tangent to the curve is being taken at the initial point. The initial rate of the reverse reaction, K negative 1, is going to be much greater than the forward reaction. Okay, so this is K1, then this is K negative 1. Okay, and so I'm not going to draw another line tangent to the curve, but notice that at some point these two rates will converge, and this is where the system has reached a state of equilibrium. Okay. And so how does the amount of reactants and products look like if the rate of the reverse is much faster than the rate of the forward? And so once again, let's go back to this image of the ants transporting stones. And so if the reverse is much, much faster than the forward, then there should be more reactants at equilibrium than products. And so to represent that on a graph, we're going to make sure that the amount of reactants at equilibrium is much higher than the amount of products at equilibrium. Okay, so once again, this blue line is representing the amount of reactants. And this purple line is representing the amount of products. Okay. And so when the rates finally converge, this is where the chemical system has reached a state of equilibrium. And so this is the type of graph that you guys would observe if the rate of the reverse is much greater than the rate of the forward. And so at equilibrium, the amount of reactants is going to be greater than the amount of products, which is once again described by this graph. So notice that the blue line represents reactants, and I can go ahead and trace it back to here. So that point is much higher than this point. Okay, and the purple line represents products. All right, so we have 3 different scenarios overall, and these are the types of graphs that we're going to observe under these different conditions, right? And so if the rate of the instantaneous rate of the forward and reverse are equal, then the amount of products and the amount of reactants and amount of products at equilibrium is roughly equal to each other. So if the forward reaction predominates, then there should be more products than there are reactants. And if the reverse reaction predominates, then there should be more reactants than there are products. All right. So that leads us with our last slide for this specific lecture video, and that's this idea of dynamic equilibrium. And so for one to achieve equilibrium, for a chemical system to reach equilibrium, once again, the rate of the forward and the rate of the reverse must be equal to each other, which is once again observed by this line, and this line. Now, this is the time where the reaction appears to have stopped. And you guys have seen this in lab, especially like, for example, precipitation reactions, right? So let me just move this slide down. So when you have 2 aqueous solution, you mix them together, all of a sudden you get this precipitate, and it appears that the reaction has stopped. But what dynamic equilibrium tells us is that both the forward and reverse reaction is still occurring. It never ceases. So all of these reactant particles and all of these product particles, they're still colliding, and they're still producing reactants and products. But since the rate is the same, the net concentration of reactants and products do not change over time. That's why we physically see no change in the test tube for example, a precipitation reaction or something like that. However, dynamic equilibrium tells us that the reaction has not stopped. It's still occurring on a molecular level, but we just cannot see any physical changes because the rates of the chemical reaction between the forward and reverse have kind of converged. And so, looking at this specific precipitation reaction, since the production of lead to iodide is predominant, then we can assume that for this specific example, the rate of the forward is going to be much greater than the rate of the reverse. And so this is the reason why we see a lot of precipitate that's being formed, just because at equilibrium, the rate of the forward reaction is much faster than the rate of the reverse. And the graph that best represents this in terms of the concentration of reactants and products would be this type of graph, where I'm going to go ahead and extrapolate this line backwards here. We have B representing products. So there is a higher concentration of products than there are reactants. Okay. So here we have a lower concentration of reactants. But once again, dynamic equilibrium tells us that for these types of reversible reactions, the reaction does not stop. It appears to have stopped, but in reality, the forward and reverse reaction is still occurring on a molecular level. But there's no net change in the concentration of reactants and products once the chemical system has achieved a state of equilibrium. All right, so hopefully you guys have a stronger understanding of chemical equilibrium. So from here on out, we're just going to go ahead and start quantifying it. All right, I'll see you guys in the next lecture video. Bye.